Voltage transformer is on the basis of Lenz's law, and based on what we've learned in general physics. When current on the left part of the voltage transformer, which called primary coil here, changes, and according to Lenz's law, magnetic field changes accordingly. And let's move on to the right hand side of the voltage transformer, which called secondary coil. When magnetic field changes, change in magnetic field leads to change in current on the output circuit. So we could get an AC power supply on the secondary coil, and the ratio of the number of the coils in primary and secondary coil is proportional to the ratio of the voltage.
Hello everyone, if you want to know how the circuit works, let's have some physical derivation. First, let's draw a RC integrator circuit. To calculate the time in the circuit, we need a conversion in the circuit before it can be used. Our group used resistor and capacitance integrator to convert the output into ramp signal waveform. First, we need to derive the square wave of the circuit using KCL, Kirchhoff current law, to get the following formula. By this derivation, you can get the following relationship. From this, we can see that output terminal is integration of the input terminal. Next, by theoretical calculations, it can be concluded that the square wave is a ramp wave after integration, so we can use this feature to value the time. We can set a value as long as this value, the output will have a change or move. But we still find out that the output voltage of the above circuit is too small, so we will use an amplifier to amplify the voltage. According to the calculation formula of the amplifier, it can be used to adjust the output magnification. By the simulations results, the output voltage amplitude of the RC circuit is about 0.6 volts. We probably need a magnification of 10 times. So according to the amplifier formula, V out equals to 1 plus R2 divided by R1 multiply V in. So a circuit with R2 divided by R1 of 9 times is needed. After combining the two circuits, we can get the circuit part we need.
We use clipping circuit to control the output voltage by connecting a resistor and a diode in series. The output voltage is the voltage of the diode. We assume that the diode satisfies the constant voltage drop model, which means the voltage drop is 0.7 volts. Then we can see that the output voltage won't be higher than 0.7, even though the input voltage is still increasing. For the second circuit, the two diodes are put in opposite directions. If the input voltage is positive, then the diode of the right-hand side will be cut off. Only the left-hand side will work. As mentioned before, the maximum value of the output voltage will be 0.7 volts. When the input voltage is negative, the diode of the left-hand side will be cut off, and this time the diode of the right-hand side will work. Now the minimum voltage of the output voltage is minus 0.7 volts. And the same principle can also be applied to sine wave. In the graph of the waveform, we can see that between minus 0.7 and 0.7 volt, the magnitude of the output voltage will equal to the input. When the input is higher than 0.7 or lower than minus 0.7 volts, the circuit will clamp the voltage. So we can control the range of the output voltage to stay between minus 0.7 volt and 0.7 volts. In our circuit, the input voltage is an AC voltage source, and the magnitude is 10 volt as we reduced it before, and the frequency is still 60 Hz. And the picture shows the result of our LT-SPICE simulation. As you can see, we successfully clipped off the part which the magnitude of the voltage is above 0.7 volts, and we transformed the sine wave into square wave so that we connect the output voltage to the motor, and the gear of the motor will push the clock to rotate. The reason why we need to convert sine wave to square wave is because if we just use sine wave, then after integrated, it will simply become a cosine wave. But if we use a square wave, then after the integration, we will get a triangle wave. Then we can make use of the triangle wave because we can define a specific threshold value so that the motor will rotate as long as the voltage is higher than that threshold value. And for every 1/60 seconds, the motor rotates. So in this case, we will be able to make a clock by using gears with different amounts of tooth to let the pointer rotate for every 1 second. And that's how our clock works. Now I'm going to introduce our gears and component. These pictures are the component we designed using CAD. The first one is the base, and the second one is the pointer of the clock, and the others are the component that push the pointer to rotate, which the driving force is the motor. And after construction, we eventually have our clock.
Now I would like to show the simulation of the clock design. It is implemented using Python. We will run the program to see how it works. First, we see the ideal clock model. It is a simulated clock, where the minute hand is a cyan one, and the second hand is a magenta one. Now we remove the board to see the detailed structure of the model. The axis of the minute hand is embedded in the green internal gear, and that of the second hand is embedded in the red gear. Note that the number of the teeth of the green gear should be 60 times larger than that of the green gear, but seemingly Python is not able to draw the gear with too many teeth. We set the ratio of the number of the teeth to be 10 instead of 60. Now, we talk about the direction of the gears. The red gear, the yellow gears, and the green gears rotates in the same direction, while the orange gears rotate in the reverse direction. The rotation of the magenta axis is driven by the motor, and thus the red gear is driven, and the orange gears are driven, and then the yellow gears, the green gear, and finally the cyan axis embedded in the green gear. Now we are going to introduce about the physical principle of the rotation of the gears. The ratio of the number of the teeth of the red gear, orange gears, yellow gears, and the green gear in our realization would be 1 by 1, 1 by 1 by 60. As the number of the teeth of the gears is proportional to the angular velocity, the angular velocity of the red gear, orange gears, yellow gears, and the green gear in our realization would be 1 by 1 by 1 by 60 as well. Let's take a deeper sight to the graph. The gray cuboid denotes our design that can transmit a pulse per second and is connected with the motor, which is a white cylinder, and the motor is a source to bring the motivation to the clock system. Let's take a look at some graphs related to our innovation. Here is some graphs about our innovation. The first one is the VT graph. The graph is generated based on the dataset here. This is a dataset about the blue line, and this is the dataset about the red line. The blue line is the integral of the red line, and the red line is the input signal being rectified. In the ideal situation, the red line would be a square wave, and the blue line would be a ramp. The second and the third graph are the circuit of our innovation. We just draw the two graphs by matplots. The last graph can generate the square wave, and the middle graph is to take the integral of the last graph. Here is our code.
We've made some revision to our project. In our midterm elevator pitch, we mentioned that we might use an LC circuit to realize our circuit, but based on the simulation result, it's been a hard time for us to find a 10 Henry inductor, so we decided to replace it with an RC circuit. Same result, more easier to implement, and of course a lot more cheaper. And in our midterm presentation, we mentioned that we haven't decided to use either 3D printing or laser cutting to realize our gears, and we finally reached a consensus that using 3D printing to realize our gears. We decided to build a clock in the beginning, and it turned out that we've had a really hard time discussing the topic, and we finally reached a consensus that using AC current to realize the design is the best choice. And the core value of our project is basically focused on two predominant points: easy to use and easy to build. And in our opinion, AC current is the most convenient way for us to reach, since electric socket is everywhere, and of course the implementation of our clock will not be complicated. And as I mentioned, it's quite simple to use a clock directly plug it into the electric socket. We divided the clock into several parts, and after a semester of hard work, we reached the goal we set at the beginning of the semester.
Participating in this project with lacking knowledge related to physical implementation such as circuit diagram, I am really fortunate to be assigned the tasks such as Python animation and to plot some results about our innovation. We distribute our tasks well. Everyone gets his strengths used in our work. However, I still learn a lot of knowledge based on not only differential equation, but also other classes such as electronics.
During this semester, I've learned a lot from the differential equation class, and we faced a lot of difficulties while working on the final project, but we eventually overcame those things. And I think the whole process, it was very interesting and inspiring. And also, I have to say thank you to all of my teammates because it is impossible for me to finish the project without you guys.
On the road to finish our project, we've already faced a lot of difficulties. And in this class, and we use a lot of tools to solve our project. Like we use Python to simulate our circuit, and it's really been a hard time to build and spice using Python. And I'll talk about the most important part. And we build the gears in a hurry, so we don't have permission to. There's 3D printers in NYCU, so we made someone who have permissions and who have access to 3D printers in Tsinghua University. So, and when I look back from this semester, and I did learn a lot of things. For example, using Python or a lot of other softwares to solve our problems. And so, thank you, Professor Remy and TA Gracious.
In the production of this project, I learned a lot of manual skills and how to find appropriate value of resistor and capacitor in simulations. So I think this project is very meaningful to me, and during the production process, I learned how to properly match teams, communication, and collaboration.